Good day, learners. Welcome back to our chemistry class. In today's class, we are going to be looking at volumetric analysis. This class is going to be a series until we get to titration. Until we get to titration. Just before we proceed, if you are a new member on this channel, kindly subscribe to my channel and click the notification bell. When you click the bell, it's going to give a prompt. Click on the personalize so that you can be seeing my lessons subsequently. Now, let's dive in properly. Volumetric analysis, from that particular word, volume, it involves measuring the volume of reactant substance. During a chemical reaction, reactants are those at the left hand side, while the products are those at the right hand side. So, when we look at these reactants here, sodium hydroxide and HCl, they are the reacting substances here, they are the reactants. So, when we are trying to measure the volume of the reactants in this chemical reaction, we are describing volumetric analysis. Now, this does not mean that we are only dealing with liquids. It can be a solid, like in this example too. Sodium triisocarbonate 4 reacting with hydrochloric acid. Sodium tricarbonate 4 will involve weighing using our weighing balance. Why? HCl will involve measuring the volume, while sodium tricarbonate 4 will involve the measurement of its mass. The main objective of volumetric analysis is to quantitatively measure the volume of the reactants reacting in the chemical reaction in order to obtain the stoichiometric ratio after the chemical reaction. So, in turn, we are going to get a balanced chemical equation. Now, the next one we look at is how do we prepare these substances in the laboratory? Mass concentration in gram per dm cube is equals to molar concentration in mole per dm cube. A standard multiplied by molar mass is a solution of so from here we can get our molar concentration solution in which the concentration is mass concentration in gram per dm cube over molar mass in grams per mole. A standard solution. The second one we talked about is expressed either in gram per dm cube or in mole per dm cube. A standard solution, if you express gram per dm cube, we call it mass concentration. What is a primary standard? In mole per dm cube. A primary standard this as is a solution with high this mass concentration and molar concentration can be and this primary standard it has some characteristics. One, they are anhydrous, they are not deliquescent, they are not hygroscopic, and also they are soluble in water. These characteristics describe primary standard, and this standard solution can be prepared from this primary standard. Examples of primary standard are anhydrous sodium triisocarbonate 4, benzoic acid, ethane dioic acid, and so on. These are prepared in a high state of impurity. These are examples of primary standard. Anhydrous sodium triisocarbonate 4. 2. Benzene carboxylic acid, which we know as benzoic acid. 3. Potassium hydrogen phthalates. Then the last one is ethane dioic acid dihydrate. When we look at this last one, there's a dihydrate here. And we said that one of the characteristics of primary standard is they are anhydrous. So why these two dihydrates? This particular substance, it is non-efflorescence, meaning that it does not lose its water of crystallization when being exposed. Because of this, it fits into this primary standard. Now, what are the methods of preparation of standard solution? Standard solution of a primary standard can be obtained or can be prepared using two methods. The first one is the weighing method, and the second one is dilution method. Now let's look at this weighing method. The first method we're going to look into is the weighing method. Suppose we have 250 centimeter cube of a solution. of 0.100 mole per dm cube anhydrous sodium triosocarbonate 4 is to be prepared. Let's look at this. We want to prepare 0.100 mole per dm cube of anhydrous sodium triosocarbonate 4. This is a solid substance. And for a solid substance, we talk about the mass or the mass concentration and not the molar concentration. So we want to use this molar concentration and the volume to get the mass concentration. Now, what are we going to go into? What mass are we going to measure? Now, the first thing is to convert this mole per dm cube into centimeter cube to change it into mass. If you could recall, in one of our class, when we're talking about the mole concept, let us realize that here now we have volume. We are given the volume of the solution to be 250 centimeter cube, and we are given the concentration to be 0.100 mole per dm cube. Mole per dm cube. From this mole concept, our number of mole is going to be equal to concentration times volume. That is one. Secondly, our number of mole is going to be equal to mass over molar mass. And verily, what we want to obtain is the mass of this substance that we are going to weigh in order to standardize it, to get a standard what? Solution. Now from here, we can equate these formulas together and say N equals to N. So we have CV equals to mass over molar mass. Then our mass will equals to CV multiplied by what? Molar mass. Now, we know our concentration, we know our volume, which will be converted into decimeter cube. Then we can calculate our molar mass from this. Now, let's get our molar mass. Molar mass of sodium triosocarbonate 4. Atomic mass of sodium is 23 multiplied by 2 plus atomic mass of carbon is 12. Atomic mass of oxygen is 60 multiplied by 3. So we have 46 plus 12 plus 48. When we do everything together, we get 106 gram per mole. From here, you can now substitute into this value, mass equals to CV multiplied by molar mass. In some textbooks, this molar mass will be denoted with capital letter M. CV capital letter M. Now, our C concentration that we have here is 0.100 multiplied by our volume is 250. And it should be converted to dm cube because our concentration also is in what? Mole per dm cube. So we have to change this to dm cube by dividing by 1000. That is 250 divided by 1000 multiplied by the molar mass we have now is 106. So let us multiply and we divide. So we have 2.65 grams. So this is the mass of sodium triosocarbonate 4. Now, so the first procedure is we are going to weigh the mass 2.65 gram on a weighing balance. We take a bottle or a petri dish, we put it on the weight to know the actual weight of that particular petri dish. If it is 0, it means we are going to add 2.65 grams of sodium triosocarbonate 4 on it. Then, if it gives us a weight, let's say the weight of that dish itself is 1.2 grams. And we want to know the weight of 2.65 grams of sodium carbonate. So we are going to add this together plus 2.65 grams. This gives 3.85 grams. Meaning that when we are adding sodium triosocarbonate 4 into it, we are going to get to the weight of 3.85 grams because we have to take away 1.2. Don't forget, 1.2 is the normal weight of our petri dish on it, or the bottle we put on it. 1.2. And we want to know the weight. We want to measure 2.65 grams. So when you are now putting this salt on it, when it gets to 2.65 gram, it is not the actual weight. It has to get to what? 3.85 gram. So when we now obtain our weight, what is the next step? We pour this sodium tetracarbonate for 3.85 gram into a beaker containing 250 centimeter cube of water. That is, we have a beaker containing 2 centimeter cube of water. We add 3.85 grams of that salt. Then we stir very well to dissolve. And sometimes you have to warm it in order to dissolve. After completely dissolved, we transfer this sodium tricarbonate solution into a volumetric flask. Then we top it with distilled water to the 1000 centimeter cube or 1 dm cube mark. In this case, we have prepared our standard solution by the method of what? Weighing. Now, let us look at some examples to support this method. Example 1. Calculate the mass of hydrated ethane dioic acid needed to prepare 5.0 dm cube of 0.105 mole per dm cube solution. Don't forget, we want to get the mass of hydrated ethane dioic acid. To get the mass is unknown. Needed to prepare 5.0 dm cube. Anything in dm cube is volume. The volume given is 5.0 dm cube of a 0.105 mole per dm cube solution. Anything in mole per dm cube is our molar concentration. Concentration equals to 0.105 mole per dm cube. Don't forget, we are given the molar mass of hydrated ethane dioic acid. The molar mass, my mm, equals to 126 grams per mole. From here, our mass equals to Cv multiplied by molar mass. So from here, our concentration is 0.105 multiplied by our volume 5.0. Our molar mass given here 126. So let us multiply. So what do we have? We have 66.15 grams, approximately to 66.2 grams to 3 significant figures. Example 2. If 4.16 grams of barium chloride were dissolved in 200 centimeter cube of water, calculate the concentration of the resulting solution in mole per dm cube. Calculate the concentration. So the concentration is going to be the molar concentration. That is, if 4.16 gram mass of that barium chloride is given as 4.16 grams were dissolved in 200 centimeter cube of water. Volume of water is 200 centimeter cube. Then calculate the concentration of the resulting solution. Concentration of the solution is unknown. Don't forget, we are given the molar mass of barium chloride to be 208 grams per mole. Now I want to calculate the concentration. If you can recall the formula that says mass equals to Cv multiplied by molar mass. So our concentration that we want to get will now equal to mass divided by volume times what? Molar mass. So our mass given here, we have 4.16 gram over the volume. Our volume here is in centimeter cube. Let us change to decimeter cube. Let us divide it by 1,000. 200 divided by 1,000. So we have 0.2 dm cube. So applying this here, our volume now is 0.2 multiplied by our molar mass here is 208. So our final answer 0.100 mole per dm cube. So this is how to calculate the concentration using this formula. Example 3. An eyedropper is calibrated such that 20 drops are required to deliver 1.0 centimeter cube. Calculate question A, volume of 1 drop. B, amount of base in 1 drop of a 0.100 mole per dm cube sodium hydroxide solution. Now looking at this, talking about an eyedropper in which 20 drops of it will give us a volume of 1.0 centimeter cube. Then 1 drop will now give us how many volume? So we are going to use a first principle method, question A. 20 drops gives 1.0 decimeter centimeter cube. Okay. Now, calculate the volume of 1 drop. So 1 drop we give, let's say x. First multiply 20 times x. 20x is equals to 1 times 1, 1. To get my x, I have to divide both sides by 20. X will equals to 1 divided by 20, which is equals to 0.05. Is under centimeter cube, So which means 1 drop will equals to 0.05 centimeter cube. Second question is amount of base in 1 drop. Amount of base in 1 drop. Amount is n of that base, which is unknown, in 1 drop. And 1 drop has a volume of 0.05 centimeter cube. The volume is 0.05 centimeter cube when the concentration equals to 0.100 mole per dm cube. So in this case, we can get our amount from our previous formula that says N is equals to CV. Then our concentration is 0.100. Our volume is 0.05. So when we multiply, what do we have? 0.005 mole, or 5 multiplied by 10 raised power minus 3 mole. So this is how to do a simple calculation using a weighing method. We are going to continue in our next class when we're talking about the dilution method. Just before we leave, if you are a new member on this channel, kindly subscribe to my channel and click the notification bell for my subsequent content. And don't forget to share, like, and comment as we leave. So I'll be glad if you can lay your hand on the exercises coming shortly.